Hello everyone, good morning or good afternoon, and welcome to our presentation. As you can see on the screen, today we will be focusing on semantic analysis of Twitter data using machine learning. We will deep dive into sentiment classification and model evaluation. And this is presented by my teammate Muntasir and myself. Let's get started. Okay, so let me first give you a little bit of overview of our project. So basically in social media sites like Twitter, sentiment analysis is at the front line of analyzing feelings and viewpoints in textual data. The fundamental goal of this project is to create an advanced model that can differentiate between three different emotions: positive, negative, and neutral. We hope to offer a prism through which social trends, public opinion, and various viewpoints may be comprehended and measured by examining Twitter data. Okay, now that we have a little bit of overview of our project, let's get to the project goal. The objective of our project is to develop a tool capable of monitoring reactions and opinions of individuals on Twitter and conduct sentiment analysis on the gathered data. This tool will offer real-time monitoring capabilities and will visually represent the analysis results through graphical plots. By doing that, we aim to provide users with a clear understanding of whether the prevailing sentiment towards a company is positive or negative. The main goal of this project will be general semantic analysis to help in making decisions. Okay, now that we have a little bit of overview of our project, our goal, let's get to the semantic analysis step part. The first part is data preparation. This step deals with collection of Twitter data and involves pre-processing steps to make data suitable for our analysis. And then we used two methods. First one is LSTM. This step deals with analysis of Twitter posts using LSTM approach. Also, we used another method called Robusta. This is the optimized version of BART. This is known for its robust performance and often results in better understanding and contextualization of language. Okay, so we talked about our project overview, semantic analysis steps. Let's get to the data part. Okay, so we used two important data sets: Twitter training and Twitter validation safety, which are thoroughly examined at the start of our exploration. This dataset study reflects sentiment dynamics in the real world on a platform as significant as Twitter. And these collections of tweet texts which have rich and varied emotion levels. This is veritable gold mine of real world feeling expression. Okay, after this overview, let's get to the data loading and exploration part. So the first stage of our investigation was to import and manipulate data efficiently. An initial analysis of our dataset provided informative glimmers into their composition, ranging from distinct tweet IDs to the complex word arrangement, which are tweet text and associated sentiment classification. I would say this preliminary investigation was very essential in terms of groundwork for more sophisticated methods of data analysis and data processing. Okay, now let's get to data pre-processing, renaming, and cleaning part. The foundation of any successful machine learning project is data preparation, definitely. Our strategy was twofold. First, we renamed data frame columns to more understandable terms like text ID, location, sentiment, and text to improve accessibility and clarity. After that, we started a thorough data cleaning procedure to guarantee the data's impeccable quality to enable precise, trustworthy machine learning prediction. Okay, so after that, we did some work on missing values. In the field of data science, handling missing values is very important step. And we thoroughly searched both datasets for any missing or null values as part of our inquiry. After further examination, the whole dataset with no missing values was discovered. We confirmed that the accuracy of our data and the dependability of the analysis. And then after we handle our missing values, that loading exploration part, we after assigning names to each column, basically the sentiments were extracted for each tweet. So if you see in this bar graph, it can be seen that the negative tweets right here are the highest. The sentiment irrelevant, there is no use of that. So what we did here, we removed the sentiment irrelevant to increase the effectiveness of the predictive model. Okay, so that's up to our EDA part. Let's get to the introduction to tokenization and vectorization. So two essential preparation steps, which are very important for text data. By dividing text into smaller chunks, tokenization makes the textual maze easier to navigate. And in terms of vectorization, it converts these tokens into a numerical language that can be processed and understood by machine learning models. And when these two combine, they turn the unstructured raw material into a refined format. Okay. So we talked about our project overview, our goal, data exploration, EDA part, and let's get to the method part. So our first method that we use, LSTM, the long short-term memory model, which excels at handling sequential and time series data. This is the brains behind our sentiment categorization task. The architecture of the model is meticulously built with multiple layers and nodes specifically incorporated to capture and handle the temporal dependencies, which is present in textual data. So the purposeful selection of LSTM was to take advantage of its ability to retain and apply long-term information in data, which is really important component for efficient sentiment analysis. Okay, so we have little bit of overview of our first method. Let's get to the model development part for LSTM. So there are three steps involved: model building, model training, model evaluation. LSTM networks are particularly suited for semantic analysis because it's their ability to process and make predictions based on long sequences of data. Unlike traditional neural networks, LSTMs have a unique structure that allows them to retain information over long periods, making them ideal for understanding context and the meaning of words in longer text passages. Okay, now from this point, I'm going to hand over this to my teammate Muntasir. Go ahead, Muntasir. The floor is yours now.
Yes, thank you, Safia. Yes, the first model we used is the long short term memory model, LSTM. We made our LSTM model by layering different parts, each with its own job. First, we have a layer that turns word into numbers. Then we add some randomness to make the model less likely to memorize and more likely to learn. We use two LSTM layers to understand the order and importance of words in a sentence. In the end, we have a layer that decides the category of the text. We also applied dynamic learning rates to be updated during the training to optimize the process. The accuracy is good, around 97. Validation accuracy is good as well, around 88. Based on the confusion matrix, the outcomes are promising, though there is a slight confusion in telling apart positive and neutral sentence. We can see here between 0 and 2, the number is high compared to the other numbers. The second model we use is a specific version from BERT, which is an optimized version model designed to improve its performance. BERT is a pre-training MLP model developed by Google to help computers understand human language better. It is based on the Transformers architecture, which uses mechanism called attention mechanisms. These allow the model to focus on different parts of a sentence as needed to understand the relationships between words, regardless of their position in the sentence. BERT can be fine-tuned with additional data to be customized to specific tasks like semantic analysis, question answering, or language translation. This is what we did. The outcome is good, achieving around 97 accuracy and 92 validation accuracy. The visualization shows a notable enhancement in accuracy along with a reduction in errors. This is what we have about the code. Thank you.
Thank you, Montaser. Okay, so let's talk about the challenges, conclusion, and future direction. So one of the most significant challenges we faced was the BERT model's apparent inability to effectively differentiate between the various sentiment classes. But after we implemented RoBERTa, which is an optimized version of BERT, our model showed improved performance. Our machine learning model exhibits substantial potential in addressing the issue of identifying positive and negative. The model's high accuracy, precision, and recall and F1 score suggest its effective utilization in various applications, including social media sentiment analysis. The model can accurately analyze public opinion on various topics or brands based on social media posts and comments. In summary, our machine learning model has demonstrated remarkable effectiveness in identifying positive and negative instances of the target sentiment. Its high accuracy, precision, and H1 score make it a valuable tool for sentiment analysis tasks. And as we continue to optimize our model, we are very confident that it will play an increasingly significant role in various real-world applications. And that's all. That's all for today. This is our references, and thank you everyone for your time. We really appreciate to get this opportunity to present this to you. Thank you.